So if you wanted to teach today's computer vision algorithms about the scene, you'd probably have to do it with a lot of explicit labeling. You'd have to tell it that this carpet is soft, that this bubble wrap is crinkly. But I think we'd all agree that the way that humans learn involves a lot more unsupervised learning. And one of the major differences is in the way that we learn from manipulating the objects around us and observing how they respond. For example, this is a video that one of my co-authors recorded. This is Ted Adelson's daughter when she was younger. And you can see that right away she starts poking, prodding, and crinkling this bubble wrap. And it's a very multimodal kind of exploration. She seems very interested in feeling the bubble wrap, later tasting the bubble wrap. And most interestingly to us, she seems to be interested in listening to the sounds that the bubble wrap makes when she interacts with it. And indeed, you can learn a lot about objects by listening to the sounds they make. This is an audio clip we recorded, and I think you can tell a lot about the scene just from it. And when we pair up this audio with its corresponding video, we can start to associate objects in the visual world with their physical properties. We can tell from the sound of hitting metal and concrete that they're hard, from the sound of hitting these leaves that they're soft and that they scatter, and we can tell from scratching this concrete that it's rough. More generally speaking, when you perform an action, the sound that it makes in response is a signal that tells you about what happened. And in a similar way to the way that humans learn from these interaction sounds, we'd like to train algorithms that can learn from them as well. And so this leads to a natural recognition problem. We can just take a silent video like this one, and we can train an algorithm to predict a plausible soundtrack to go along with it. The idea is that by training an algorithm to predict sounds that are visually indicated by actions and videos, then it'll implicitly have to know something about the world. In particular, this is a material understanding problem, because in order to produce the right sound, you need to know what materials are being interacted with. But unlike traditional material recognition, we don't explicitly tell our algorithm about materials. It just has to learn about them by finding patterns in the audio-visual signal. And in this way, it's very similar to recent work in unsupervised or self-supervised learning that learns from unlabeled video and images. In our case, though, the learning happens from solving a multimodal prediction problem. We're predicting sound from video. And this idea also of learning from interaction is something that's been studied in a robotics context before. But instead of having a robot perform the actions, we did it ourselves. We just went around with a camera and a microphone and a drumstick, and we hit and scratched the different objects that we found. And we usually recorded this in quiet places like libraries and basements and parks. And we used a drumstick to do this because the drumstick makes a loud, consistent sound. And the resulting dataset has about 1,000 videos in it. We call it the greatest hits dataset. And to give you a feel for the kind of sounds that are in the dataset, here's a sample of sounds. So we had a lot of fun with this. And you can get the feeling that different materials are making different sounds, and we'd like to confirm this. As a first check, we'd like to confirm that you really can predict material and physical properties from sound. And so to do this, we took all the impact sounds in our data set, and we computed simple audio features for them. We used a cochleogram representation of the sound. We get this just by taking the waveform, filtering it with a bank of filters tuned to different frequencies, and then taking the envelope of each one. And then using the sound representation, we can start to see differences between different materials. For example, the average cloth hit tends to have a lot of low frequency energy, whereas rock tends to have a lot of high frequency energy. It's a higher pitched sound. And we can make this idea more precise. We can just train a linear SVM on these sound features, and we see that indeed this is a very good representation. We're able to the classifier gets about 46% class averaged accuracy on a 17-way classification problem. And this is in the ballpark of what you'd get if you trained a visual classifier with CNN features. So this suggests that, as we suspected, that these sounds are informative about physical properties. And now we'd like to predict audio from video. And the way we're going to do this is by regressing these cochleogram features from an input video. And we're going to do this using a recurrent neural network. And it has a fairly standard design. We represent each frame of the video using convolutional network features, and then we regress the corresponding sound features at each time step. And so during training, we minimize the regression loss that penalizes the difference between the predicted and the ground truth sound features. And then there are a few implementation details. For example, we use a 3D ConvNet that does convolutions in the time domain, and we also generally pre-train the model from ImageNet. So once we have these sound features, we'd like to generate a waveform that someone can listen to. And the way we're going to do this is by finding example sounds in our data set that have sound features that are similar to the ones that we predicted. We detect places that have amplitude peaks. These likely correspond to impact sounds. And then we do a nearest neighbor search using the neighboring sound features, and we transfer the best matches. So that's our algorithm. We go from images to audio features using a recurrent neural net, and then we go from these audio features to a soundtrack by playing examples from our data set. And so now let's listen to some of the soundtracks that our model produced. This is a case where it works relatively well. I'm just going to play the sound that our model predicted. So we can visualize the exemplar sounds that the model is transferring, and when we do this, we can see that it seems to be distinguishing between the leaf sounds and the dirt sounds. And the model generally works better on outdoor scenes. The materials there have a more consistent appearance, and the geometry is usually more consistent. We can also see how it does on indoor scenes. In this case, it tends to get the sound right, but it misses a few hits. And sometimes the algorithm fails. I'm going to play an example. Maybe you can tell what's going on here. So what's happening is that when the drumstick moves upward and abruptly stops, the algorithm thinks this is a hit. And this is likely because it requires a little bit of high-level knowledge about the scene to know that the drumstick's actually stopping in the air and that it's not striking a surface. So those are some of the soundtracks, but we were interested in evaluating how plausible our sounds were. And so we trained a variation of this model that just predicted sound for individual impacts. And then we did a human study. And the way this human study worked was we'd play a video with two different soundtracks. One of the soundtracks was real, the other was predicted by our model. And then we asked them which was the real sound. So let's do one of these. I'm going to play a video with two different sounds, and then you can tell me afterward which was the real one. Okay, raise your hand if it was the one on the left. Raise your hand if it was the one on the right. So this is a particularly hard example. The real sound was the one on the left. And I think this illustrates how it's often not that hard to fool people. You can just play a sound that is prototypical of the material category and that sounds pleasing to the ear. And a lot of times this will fool people. And as an aside, this is something that sound effects engineers have studied. A lot of times when you hear a sound in a movie, it wasn't really recorded on site. It was made by engineers later on. And you can think of our algorithm as a kind of automatic sound effect engineering. Okay, so once we can use this procedure to evaluate our model, and when we run it on a lot of videos, we see that it fooled people about 40% of the time, which is significantly more than a model that just played a random impact sound. That fooled people about 20% of the time. And you should note that it was still fooling people some amount, especially for a lot of these hard materials. So, and then in between was a baseline where we just used the image features and did a nearest neighbor search and retrieved the best match. That performed in between these two different methods. Okay, so these results suggest that the sounds are often plausible to human subjects, but we were curious about what the model learned, whether it learned a good visual representation and whether it learned to distinguish between different materials. So we took this classifier that we trained before, this one that was trained to predict material categories from sound features, and instead of plugging in real sound features, we plugged in sound features that were predicted by our model. And when we did this, we trained the model from scratch to avoid the influence of pre-training. And we see that indeed it learns, it distinguishes materials significantly better than chance. It gets about 23% class average accuracy on a 17-way classification problem. And we can look at the materials it does well on. These tend to be ones that have a distinctive visual appearance, like cloth, water, and dirt. And the materials that it's not able to distinguish are ones where there's a lot of ambiguity in both their appearance and their sound. These include materials like glass, drywall, and metal. So in this work we showed that sound, when you pair it up with video, can be a useful signal for learning about physical interactions. And since audiovisual data is very easy to acquire, anytime a person or a robot interacts with a scene, it generates sound. We think it'd be very useful for learning visual representations and for applications involving sound effects, and also looking into the future for studying robotic interaction. Thank you.